does your morning routine consist of? The first thing you do is probably turn off the alarm that's blaring from your phone, right? Then you might take a shower, brush your teeth, comb your hair, get dressed, have some breakfast, maybe some coffee. By now, this routine is second nature. But I want you to take a second and really think about all of the products that you use in that short time. They all have one thing in common. That's right. All of these products are made from plastic. But what if I told you that when all these products get thrown away, they damage our environment? They could potentially find their way to the ocean, the side of the road, or a landfill, and stay there for over 1,000 years. As an engineer, this should be a giant red flag. So how can we fix it? Well, recycling is always an effective way to better the environment, but what if we just change the way we make plastics? Turns out we can, and this new plastic is simply biodegradable plastic. This biodegradable plastic is meant to decompose back to the original materials from which it was made, making it a cleaner alternative for the environment. It also has other applications that are extremely useful, like use in biomedicine for drug delivery, wound dressings, and even surgical implants. But if biodegradable plastics are so great, then why haven't they been introduced in more products? Turns out there are some downfall to these cleaner plastics. They may not even be cleaner than oil-based plastics at all. Also, how much does it cost to synthesize these biodegradable plastics? If the cost is unmanageable, will it even be worth it to try to change all of the plastic we consume? To answer these questions, we need to analyze how biodegradable plastics are made.
This flowchart depicts the cyclic life of biodegradable polymers as they are made using natural chemicals that decompose back into the environment after being used. There are two main mechanisms for producing biodegradable plastics currently used in today's industry. This video depicts simplified animations of the mechanisms. Note that these are not necessarily real molecules being shown, but are simply used for visual convenience. The first type of mechanism is polycondensation of diols and carboxylic acids. Starting with the carboxylic acid, when met with an enzyme, a separation of charge occurs at the carbonyl group with a negative charge on the oxygen and a positive charge on the carbon. The diol comes in, and the slightly negatively charged hydroxyl group will form a bond with the positively charged carbonyl group. The hydroxyl from the carboxylic acid and the hydrogen from the diol will condense as water. The process will then repeat over and over again, forming a very long chain that will be the polymer. The second type is ring-opening polymerization, which takes advantage of the instability of molecules with lots of ring strain. Again, an enzyme causes the separation of charge of the carbonyl group. An alcohol attacks the positive carbon, and the oxygen in the ring takes the hydrogen of the alcohol and then splits away from the ring. This link of the chain then attacks another ring, and the process repeats over and over again, forming the entire polymer.
The two main types of biodegradable plastics on the market are PHA and PLA. PHA is created via the method of polycondensation, and PLA is created via the method of ring-opening polymerization. Both of these show promise in overcoming the shortcomings of petroleum-based plastics, but possess limitations that can make them potentially unattractive to consumers and manufacturers. The main advantage of PHAs are that they can all degrade in carbon dioxide and water, regardless of the molecular composition and physical properties. They break down via thermal degradation, which is the tendency of the components of the long chain backbone of the polymer to begin to separate and react with one another, which changes the properties of the polymer. Current applications of PHAs are water-resistant surfaces, binders, synthetic papers, medical devices, electronic parts, food packages, and agriculture. In terms of cost, PHA is more expensive to manufacture than petroleum-based plastics. High production costs, low yields, and limited availability have made it difficult for PHAs to displace petroleum-based plastics commercially. PLA is a synthetic polyester that is said to biodegrade within a year. PLA is created through bacterial fermentation, which creates lactic acid, which is then polymerized. Manufacturers tend to use PLAs more than PHAs because they're cheaper and easier to produce. PLAs also have several applications in the biomedical industry. For example, PLA is used to synthesize medical screws and plates that can be degraded and reabsorbed by the body. PLA is brittle, hydrophobic, and thermally unstable, which can lead to complications in its use outside of biomedicine. Within biomedicine, problems can arise as a degradation process creates a large buildup of lactic acid, which can be potentially hazardous. Researchers at North Carolina State University developed an equation to assess environmental costs and benefits of biodegradable plastics. This equation considered landfill, construction, operations, cover placement, gas placement, maintenance, and monitoring. They used this equation to compare the emissions for producing and disposing biodegradable plastics versus petroleum-based plastics. These researchers found that petroleum-based polymers may have a less negative impact on the environment than biodegradable plastics, which essentially defeats the purpose. This study emphasizes the need for more research into developing a more environmentally friendly biodegradable plastic. Also, recycling biodegradable plastics is nearly impossible. If biodegradable plastics are mixed with regular plastics during recycling, the regular plastic's integrity will be compromised. This can be especially dangerous with food packaging, as degraded chemicals and external contaminants can enter the food, which can be dangerous to human health. From a business perspective, biodegradable plastic manufacturers must expect 2 years of loss before reasonable profit can be made. Therefore, companies are hesitant to invest in such a risky product. Also, current biodegradable plastics do not make a significant enough impact on the environment to be worth the economical uncertainty.
Overall, biodegradable polymers have the potential to be the answer to the environmental and economic issues of the unstable and unsustainable oil market. However, at the present time, the existing biodegradable plastics are not effective enough to become prevalent in the current industry. Polymers such as PHA and PLA are not cheap enough to appeal to many customers. Additionally, current biodegradable polymers do not effectively handle environmental concerns, as recycling can require meticulous effort and the need to recycle them limits their usability in the market. The reaction mechanisms of ring splitting and polycondensation open up a whole new realm of possibilities, but more time and effort is needed to find the biodegradable polymers that, when produced, will actually make a positive impact on society. More research needs to be put into biodegradable polymers in order for them to become a feasible alternative to petroleum-based products in America and around the world today.